Well, hello, NATR 346 class. This is sort of the beginning of another module in the class where we get into the hydrologic cycle in more detail and we start talking about water budgets. So far, the first lecture was just about how we can get water vapor to condense and fall as precipitation. And then if it falls as precipitation and lands in a watershed, how to calculate how much water that is. So I hope that is all making sense to you. Now we're going to dig a little bit deeper of different pathways that the water can take, including recharging groundwater and having groundwater recharge rivers and lakes, surface runoff, and then this plant uptake. On this diagram, it's a small arrow, but we're going to find out that that should actually be one of the biggest arrows. So we're going to get into some technical terms here. Maybe you've heard of these, maybe not. That's fine. There's no prerequisites here. The first term here is infiltration. So if the rainfall comes out of the sky and hits the ground, if the soil conditions are right, if you can imagine if the rain falls on a gravel or a sand or loose material, then it has an opportunity to go from the land surface and go down underneath the land surface. That's called infiltration. After it infiltrates, then it percolates. This is another term, it percolates down through the unsaturated zone here, eventually recharging groundwater. We've already covered in the first examples when it rains and the ground can't take the infiltration, then the water will then run off into a river, and in the case of that Laurel Canyon, a lot of it gets trapped by a dam. Another term here is, and see what happens to the water sometimes, is that the plants will take up the water through the roots and transpire. And this is a big emphasis of this class because a lot of our water that we collect ends up getting transpired through plants, crops, and landscaping, and that's where our biggest opportunity to conserve water is. So here's another look at the same thing, precipitation. In this case, you can see the precipitation infiltrated through the ground. The plant, in this case, takes it up, and there's moisture that comes up through the roots, through the stems, and out the leaves. If the moisture leaves through the plant, that's called transpiration. If you just have a puddle of water and it goes from liquid to vapor, that's called evaporation. Probably you're familiar with that. Another term here is if the water goes into the soil, the plant takes up the water because it's thirsty and it's growing. A lot of that water will leave the leaf as vapor, and that's called transpiration. And typically these two terms, evaporation and transpiration, are combined into what is known as evapotranspiration. And we're going to get into this a great deal because, like I say, it's a big part of our water budget. So this is a big fundamental issue. I think most of you are familiar with photosynthesis, this process where plants will take in energy from the sun, carbon dioxide from the atmosphere, and water, and grow plant tissue. And to a plant, oxygen is a waste gas, and so they breathe out the oxygen. So I hope this is good review for you. What's not shown here is that when the plant breathes out oxygen, and actually when it breathes in carbon dioxide, it by mistake also releases a lot of water vapor. It's just inefficient that way. So the way plants are built, they have an opening called a stomata, and it's literally a hole in the leaf tissue. And that's the hole through which carbon dioxide can come in and oxygen can go out. That all works great. The problem is when that opening opens up, water vapor can escape. And we lose a lot of water supply through this mechanism. So I'm going to throw a few things at you. We're going to go over them again in different ways. But here is a chart of basic home water use. This is from some studies. And you can see showers use 20%, toilets 4%, etc. Look at this landscaping. 57% of the water in a house goes to the landscape. And I'm going to repeat this a bunch of times in the class, but there's a really big difference between using water in a shower and a toilet and laundry and using it in landscaping. Because think about it. If you're taking a shower, maybe you're taking a 10-minute shower or whatever, or your toilet is inefficient and flushes at 6 gallons of flush, where does that water go? It goes down to the sewage system and it gets treated at a POTW, a publicly owned treatment works or sewer plant. They treat it to a certain standard and then they discharge it into the river. In this case, our water, when we flush a toilet, goes down to the Sacramento Regional Sanitation District where they treat it and they discharge that into the Sacramento River and it goes out into the Delta. So water that is used for showers, toilets, laundry gets reused potentially many times. And that's a very, that's a very different picture than when you take the water and you put it on the ground, the plant grows and it belches out a bunch of vapor and that water just goes into the atmosphere and is not reused. So there's a very big difference in the world of water between using water for showering, laundry, toilets, etc. versus landscaping. The same is true for agriculture. So, and again, this is just a brief intro. We're going to get into this more, but this is a water budget for the state of California from the Department of Water Resources 2018. And I'll provide a link to this so that you can study it more. I'll ask you some questions, no memorization here, but just the California Department of Water Resources studies this in great detail. So here, these are different water years. And you can see in 2011, we had a very wet year, 134% over. And these were drought years. 2014 was terrible, 56% of normal. But what I wanted you to see is the big categories of how we use water. We use it for urban, agriculture, and environment. Those are the big three categories. And you can see the magnitudes here. For urban, it's 7.7 million acre feet. And agriculture, way more than that. We use most of our water that we capture is used for agriculture. And then this is water that is left for what they call environmental. That would be in-stream flow requirements, wild and scenic rivers. We'll get into all those. But what I wanted to point out here is you can see within the urban, you've got residential interior, residential exterior. And it's the same as the chart before. It's about 50-50 roughly. So this is why this evaporation and evapotranspiration concept is so big. And we're going to be working with it quite a bit because that's, again, the key to doing more efficient landscape and therefore more efficient water resource management. So I'm going to talk more about evapotranspiration and how we can use it to manage water supply and really actually redesign landscapes. So this is a map of the state of California. And again, I'm going to make sure you have a link to this and download it. It maps out what they call reference evapotranspiration. I have a 2-page write-up on this and I'm going to hand out. I want you to read it. I'm just going to introduce it briefly. What they endeavor to do here is say the reference evapotranspiration rate is how much water would alfalfa or a sod lawn basically use every month just to keep green and happy and watered. So you can imagine that down here in the hot country, the evapotranspiration rate would be higher than up north. It's hotter and drier. The grass is going to want more water. It's going to transpire water. When it takes up water, it loses a lot through that stomata in the leaf tissue. And so what this tells you is how much water is transpired by a lawn in different places in these different zones. So here in Tuolumne, Mariposa, zone 11, over the course of the year, a sod lawn will evapotranspire 53 inches of water, several feet of water. So over the course of a year, if you had a sod lawn in this area, zone 11, you're not going to need to apply at least 53 inches of water to keep that grass happy. So this is a flyover. I hope it's not confusing. I am going to hand out a more clear explanation of what that is, but we're going to be using these rates to estimate how much water would a lawn need in Fresno versus in the Trinity. And we're going to look at different plants because this is a reference evapotranspiration for, again, a sod lawn. If we used plants that were more efficient with water, then you would end up using less water for that plant in a nutshell. It's called xeriscaping. Probably you've heard about it. We're going to get into that in quite a bit more detail. So, what I really want you to learn from this unit is, to me, if you could fill out this diagram, then we're in pretty good shape. This is actually a figure right off of last year's final. I don't know, frankly, class, how we're going to do testing in this remote setting. We're going to have some kind of timed quizzes, though. So these are the components of the hydrologic cycle that I want you to be able to identify on a crude figure like this. So A is precipitation. F is where that water decides to go underneath the soil surface. That's infiltration. If it rains too hard and fast or the ground's paved over, it'll run off. That's H is runoff. If it does make it through the soil and gets through below the root zone, let's say, of where plants are, it'll percolate. C is percolation down and recharge to groundwater. E is groundwater seeping along here at a few feet per day. That groundwater will eventually feed a river or a lake or the ocean. B is important. B is water that has infiltrated but then gets taken up by plant roots. And then this is the big term here, D, evapotranspiration. If the water gets taken up by a plant and gets belched out through the leaf as water vapor, that's a big loss of water. That's D. And then G is just water going from liquid into vapor on the water surface. That's evaporation. So I would want you to be able to do this, match these up without having to look something up, for example, just to be intuitive with what these terms are. And I'm going to be handing out some problems on the watershed now that are a little bit more involved. Before, I just said it rained 2 feet. The area of the watershed is 100 acres. So 2 feet times 100 acres is 200 acre-feet of water. Okay, that's fine. Now we're going to add a little bit more of these other components, and I'm going to say, hey, maybe half that water actually infiltrated and percolated and hit the groundwater. Now how much is left for the rivers? And maybe a quarter of that water that fell got lost, taken up by plants, and transpired away. So it'll be very simple, but just a little bit more detail in the water budget for a watershed. So stay tuned on that.